All right, in this module, we're going to start with looking at different imaging modes that we have in light microscopy, now that we've learned how to prepare specimens. And we're going to start off by examining the bright field and dark field imaging modes, which are the most commonly used in light microscopy. But let's start with, how images are formed and what allows us to use these different modes. So, differences in properties, right? So something in our image, in our specimen, has different properties. And if we're talking about differences in the properties of the light wave, they can be reflected or transmitted through, and they can also interact with the object. And this enables us to observe these objects by light microscopy. So let's look at a couple of the ways that a light wave can interact with our object. So if we have a reference, and I'm abbreviating it here, wave, and so we're going to just depict that as a simple sinusoidal wave, right? And it just doesn't, this is our reference wave, so this is what happens if no object is in its way. So now, if I try to draw the same wave, so just imagine this is the same wave, I apologize for the terrible drawing, and our image, if our object is placed here, so now things that can happen is that the amplitude could get smaller. So reduced amplitude. This is our, again, object here. So our object is placed in front of the reference wave, and the amplitude decreases. So we have that result. So that's one. So this is an amplitude change. All right. And lastly, let's look at another result. All right. So again, our reference wave in front, and then we have our object. And the other thing that can change is that the phase can change. So effectively, the fact that, for example, this peak would be right here is now a minimum. So we've shifted the wave by interacting it with the object. So this is a phase object, and we have a changed phase. So when I say phase here, I'm not referring to any crystallographic or anything like that phases in the material. I'm talking about phase of the wave. So basically, what we kind of want to see here is that there's two options we can have when we're looking at the wave. We can reduce its amplitude, or we can change its phase. Those are kind of the two ways in which we can affect that wavelength, that wave that we're looking at. However, our eye, the human eye, can only recognize amplitude changes. or wavelength. So obviously wavelength because we can detect different colors. So it does not detect the phase change. So we can't detect these phase changes in this. So obviously, if there are phase changes, something would have to be done to the light wave in order for us to recognize it in the human eye. So we need to look at basically changes in amplitude or wavelength. And so that's an important part of these imaging modes that we're going to look at. One note I will say is that there are types of imaging modes that do allow us to see these changes in phases, but we typically have to convert those phase differences into an amplitude difference so that we can see it. So we basically have special arrangements and instrumentation so that we can transform differences in phase to differences in amplitude. And we'll go over at least one example of this type. All right, now let's talk about bright field and dark field. Bright field, abbreviated BF sometimes, whereas dark field is DF. Bright field is the most common imaging mode that you're going to see. So chances are, if you're looking at a micrograph or an image from a light microscope, it was taken in bright field. In this case, the specimen is evenly illuminated. So this is by the light source. And so we can draw what this will look like for transmission, right? So that's the light going through the objects. So I've got my object here. So this is my object. And then my objective is up here. This is my objective lens. So the light is going to converge to the object, and then it's going to transmit. So it's going to go through the other side, and it's going to come from the condenser. So effectively, the light is being condensed by this condenser lens, goes to the object where it converges to that point, and then diverges up to the objective lens. And so it's evenly illuminated in this case, and so that means that a majority of the specimen is illuminated. So typically how we draw this is we draw another set of the external light may be blocked. So light around the edges is blocked. So if we see the light from top down, it would look something like this. So basically, light sort of at the very edge could be eliminated from the aperture. So essentially, the aperture is here. So that's controlling the amount of light. So we did that in order to prevent too much scattered light, which can degrade the image. So essentially, that's what this is down here, and that's why we have the light sort of at what we call oblique angles being stopped. But more or less all the light goes through to the objective. All right. So that's what we see in bright field. So dark field, or DF, we can kind of think of as the opposite. So we still have, and I'm going to just, excuse me, I'm going to draw it on this side so you can kind of see the comparisons between these two modes. So again, we have our object. We have light converging from the condenser, right? So this is still our condenser. And then again, same thing. We have divergent towards the objective. So same diagram that we had before, but the difference is in the arrangement down here. So here we have a different type of aperture that only allows this oblique light, so light from these very high angles. So only letting light in here and here. So what that does is the converse of what we saw over here. So now this middle part is all dark. So this whole middle thing is dark. And so what we see here is a ring of light, again at these oblique angles, and then dark in the middle. So this is known as a central stop. And it allows us to do dark field imaging. So we only have what we call oblique light rays. So that's what's illuminating the sample. All right. So these two images show you the differences between bright field and dark field and what you might expect. So we talked about the contrast generated from etching, and so those lines represent the grain boundary, and they're dark because that light is scattered and doesn't reach the objective, right? So it appears as dark. Whereas the others, the light is scattered in a normal fashion, and we have a light image. So the name bright field comes from the fact that the majority of the image is going to be bright, and only features where light is scattered will there be a dark image. So bright field, it's a mostly bright image. These other things, these kind of secondary phases or pores, and the grain boundaries are relief from that contrast because of scattering. So it's mostly bright. On the other hand, we just talked about dark field, and in dark field, as you might imagine from the name, is mostly dark. Since we're only illuminating the image, illuminating the specimen from those oblique high angles. So when we talk about the angle here, we're talking about the aperture angle alpha. So we only have light coming in from those oblique angles, and so that light doesn't reach the objective. So it appears as a dark. So if there's nothing special, if it's just mirror finish, we're not going to see anything. No light makes it to the objective, and so it appears as dark. So only when light is scattered, then it makes its way back to the objective. So closer in at those angles in that dark cone I drew. And so that's how we have contrast, is those scattered, the features that scatter the light bring it closer to the objective so we can see it. And so the contrast images appear light, the rest of it is mostly